Let's begin with the summary of the previous lecture. In the previous lecture, I gave you several properties of the interesting properties of the density matrix. And the first relation you should note is that when you are given some density matrix, whether one of the questions is whether you can immediately tell whether the given state is a pure state or mixed state, and the criteria is quite simple. If you know about the density matrix by itself, just square it and then calculate the trace. And then if it is a pure state, then the value will still remain as 1, while it is mixed state, it will become less than 1. And even though density matrix by itself might look a very special type of the matrix, however, it turned out that as long as your matrix satisfies only these two conditions, then they are eligible to be a valid density matrix. And then the condition is the trace should be 1, and then another requirement is that it should be a positive operator. So as long as you have these two conditions, then any arbitrary a matrix can be a density matrix, and then in principle you should be able to find out the corresponding ensemble of the pure states. And along the similar idea, many people might consider that once you are given this kind of positive operator with the trace of 1, then you might consider that there is a unique decomposition of the density matrix into the ensemble of the pure states, and that is not the case. There are many different types of in fact, the given density matrix can be decomposed into many different ensembles, and then it is not unique. Yeah, so it is not unique. However, all those decomposition should be also related to each other, and then such kind of relation can be, and then all of those decomposition can be eventually shown that they are connected through unitary relation. Another concept I also introduced was the reduced density matrix. So when you are one of the reduced density matrix is obtained by calculating the partial trace when you have given the density matrix of the full state. And then so if here I just assume that there are A and B particles, and then this one shows the full density matrix corresponding to the composite quantum system. However, in that case, we might just interested in the quantum state of the A part only, and then we don't care what happens with the B, or not intentionally, but sometimes we even don't have any access to the information about the B. So in that case, what we do is we trace out only the part of the B. Yeah, so and then that is such kind of process is called as partial trace. And then one of the interesting situation is if some states are entangled, or two or more particles are entangled with each other, or qubits are entangled with each other, then even if we started with the pure entangled state, they becomes mixed state. And then calculating the reduced density matrix allows us whether some kind of state is entangled or not. In today's lecture, and then in the next lecture, we will continue to I will continue to introduce a way to tell whether some kind of given state are entangled or not. And then if some state is not entangled, they are generally called as a separable state. And then there is a very interesting mathematical criteria to tell whether some kind of given state is entangled or not. And finally, one of the interesting application of the reduced density matrix formalism is that to use that to prove to use the reduced density matrix to prove that the quantum teleportation by itself cannot give you any information until you actually deliver the digital information of which Bell state was measured during the protocol. So let's move to the today's topic. So in today's lecture and the next lecture, I will mainly talk about whether when we are given some kind of state, whether that state is entangled or not entangled, and we generally call not entangled state as a separable state, and this is the reason why we call it as a separable state. So you are given this kind of quantum state, then you know that this one is not entangled because the quantum state of A is completely independent of the quantum state of B. So and then we call this kind of state as entangled because it looks like if we make a measurement of A, and then depending on what kind of value we obtain for A, whether we obtain 1 or 2, the value of the B measurement will be different. So yeah, this is perfectly entangled, and then we know that this is this is a well-known definition of the entangled state, and then this is one of the Bell bases. Then the next question is, what about this state? Do you think this is entangled or it is not? Well, if you look at this state for the first time, then it might not be easy to tell. So let's see, what kind of property we can think about it. Here, what we can consider is that this state actually can be factored using the except that except this sorry, not 2, not square root of 2, just the 2, and then if you just factor out for this state, then it can be rewritten in this way. And also, if we factor out this part, then it will be just 1 minus 2b like this. And then now you can see that there is a common factor like this one. So it can be, again, factored or combined in this way. So you can see that this state can be turned into the shape of the this one rather than the second form. Yeah. So even though if you see this precisely for the first time, then you might not be immediately tell whether it is entangled or not. But once you have this kind of calculation, then you can now see that this can be a separable state, or sometimes it is a separable state is called as a product state. So with this kind of decomposition or rearrangement, you can tell whether the given state is entangled or not. The problem is in many of the situations, the decision of whether it can be it can be changed into the separable state or not is not quite obvious. So for example, even if you have only so instead of plus, we might have just a minus sign here. So and then if we have only minus sign, can you tell whether this is entangled or not? Yeah, so that's not easy. And moreover, yeah, one of the example I'm going to use in today's lecture is that yeah, let's say that we have psi 4, which is yeah 2 times 1a 1b minus 1a and 2b, and yeah, we will have this 2a 1b, and finally we will have the plus 2 and 2a and 2b, like this. Can you tell whether this is entangled or separable? Well, yeah, that's not easy. And then what I'm going to show you is that this state, this psi 4, can actually turn into the shape of this one. And then what is the requirement for this entangled shape of the entangled state? Yeah, you might think that, well, these two states looks yeah, they might look similar, but there is some difference. And then the most important difference is that for the entangled state, what happens is that yeah, let's say that we have a state a qubit, and then we have b qubit, and then typically a would have some kind of basis, and then b would have another types of basis. And then yeah, I might just call this one as A1 and this one as A2, and this one as 2B, and this one as 1B, like this one. And the point is, if we have yeah, and then yeah, in principle, we can consider all 4 different combination of the A qubit and B qubit. However, the most obvious situation for the entangled state is only when we have the combination of 1A and, yeah, for example, 1B, and then there is another term which is 2A and 2B type, and then if they are added with some kind of coefficient here, and then these two coefficients doesn't have to be the same, or they don't have to have a same sign or same phase. So whatever value you have, that doesn't matter. The point is, yeah, there is no mixture of the this 1A with 2B or 3B, or yeah. So this B system might have more than 2 orthonormal bases, and then the point is, yeah, and if you have the orthonormal basis, then one of the vector in the basis will be only matched with or appear with another orthonormal vector in the orthonormal basis, and then this one does not appear with some other vectors. So if you have additional term like 1A and combined with 2B, then and then with some kind of coefficient, then it is not easy to tell whether it is a separable or the entangled state. But if you have only this kind of shape or this kind of combination, then it is definitely you can definitely tell that, yeah, because 1 and 2B 1A and 2B 2A are also orthogonal to each other, and these are orthogonal to each other. So in that case, you can immediately tell that this state can be this state is actually entangled state. So the question is, how can we turn this generally looking quantum state as into this form? And in principle, yeah, one option is, yeah, if we write the given quantum state in terms of these 1A and 2A basis, and then 2B and 1B and 2B basis, then they might look like this all the terms might just appear here. But if we can find out new basis, let's say that this one as a new basis, and then it is called as Roman numeral A. Sorry. Roman numeral A, and then the another orthogonal basis as Roman 2 numeral A, and then if you can also find the new basis, which is B's case, and then this one is B's case, then if you can find out that so if you can find out some these new basis, and then if the same psi 4 can be rewritten as something multiplied to 1a and then 1b and plus with some other coefficient with the 2a and 2b, then you will definitely, and then both of these two coefficients are not 0, then you will definitely say that they are the integrals. And then if one of them is and if only one term, one coefficient is non-zero and all the others are 0, then you will just consider it as entangled state, pure state or a separable state, and then product state. So now the question is whether we can immediately, we can easily turn this, whether, how can we, if there is any, if there is this kind of orthogonal basis, then the question is how can you find out those bases? So the way we approach is the following. We will actually consider the, here I forgot to use the square root of 10 because to properly normalize, it should be 10. Yes. This is a square root of 4 plus 1 plus 1 plus 4. Yeah, so it should be a square root of 10. Sorry about that. And then now what we are going to do is use each of these coefficients or the coefficient here as the component of some new matrix. So I will say that I will call some kind of matrix as C, and then the first row, first column component of this matrix, I will choose from the first coefficient, which is 2 over square root of 10. And then for the 1, 2 component, I will obtain the coefficient here, which is -1 over square root of 10. And then C21, I will obtain from this value, which is -1 square root of 10, and then finally 2 component, it comes from this coefficient, which is 2 over square root of 10. So this one will look like because I have the common factor of square root of 10. So let me just pull it out, and then it will look like a 2 -1 -1 and 2. And the question is whether I can find some kind of basis transformation such that this will turn into some diagonal shape. So if you can find some unitary transform or the basis transform which will change this kind of matrix into this one, that means that I will only have the non-zero component in front of this one and this one. Well, it is not exactly true because these are the original bases, and then what I have to do is find out new bases, and then for the new basis, what I can say is in the new basis, all the diagonal components will be 0, and then only the no, sorry, non-diagonal components are 0, and then only the diagonal components which appears here and here will be non-zero. So yeah, this is my goal to make this given matrix. And then if you note that this matrix is the Hermitian, then you learn that in principle all the Hermitian operator can be turned into can be changed into the diagonal shape. So that's what I'm going to do in today's lecture. So before I continue my discussion, let me review what we learned in the lecture 4. In the lecture number 4, this is a page from page 6 from the lecture number 4, and then I explained about the basis transformation of the matrix representation, and all description, what my conclusion can be summarized in this way. So what we want to do is following. So we assume that there is some orthogonal basis, and then I will call this one as the original orthogonal basis, and then they will be expressed as Arabic numeral like 1, 2, and n, and then what I want to do is transform or use a new orthonormal basis, and then I will use the Roman numeral to represent the new basis. So in this case, we know that any arbitrary vector v can be expressed as the linear combination of all these orthonormal bases, and then there will be coefficient, and then we call this one as a probability amplitude, and then it can be generally written as the sum of all the sorry, I should have the coefficient in front of it here. And this one can be also represented as the column vector like this one. Yeah, so this is the vector representation of the column vector representation of this abstract vector in this given basis. And then the general formula to obtain these values can be expressed in this way. What about the same vector in the new orthonormal basis? Then the formula or the shape should look similar to the original one, and then what is the different is the original orthonormal basis is replaced by the new orthonormal basis, and then accordingly the probability amplitude or the coefficient in front of this vector should be also changed according following the following these basis vector, and then it can be generalized as a summation of these combination. And along the same line, the column vector representation of this the same vector. Yeah, so this vector and then this vector are the same. And then in this case, we don't need to use different notation because they are these vectors are absolute object. However, the column vector representation of the vector is actually different. So because these value or these coefficient will be different depending on what kind of basis we are using. So that's why I have to use different notation to represent these two. And then just following the same argument here, each of these value can be obtained by taking the inner product between the one of the basis vector, basis vector and the given vector like this one. So this is the formula. And then the question is, how are these vectors are connected to each other? And the answer is they are generally connected through the unitary transformation or the unitary matrix. So the connection between these two can these two different representation in column vector representation in the different bases are connected through this unitary matrix, and then the relation can be summarized in this way. So the vector column vector representation in the original basis is represented as the matrix product of the unitary matrix and the new column vector representation of the column vector representation in the new basis. And then what you should also realize is that each of these components can be considered as the matrix element of this absolute abstract abstract unitary operator, which is defined in this way. And then we can also say that these values are actually the matrix representation of this abstract unitary operator in the original orthogonal basis. So and then when you are trying to figure out the matrix element of the operator in the given basis, then that's these are the formula you use. And then if you just and then in lecture 4, I explained why these will eventually look like this one. So if you note this format, then each of the column actually represent the new orthogonal basis in the which is represented as the or in terms of these orthonormal basis. So if you consider that this one vector is is this vector, then if you replace this one with if you replace this v with one of these, then they will just appear like a Arabic numeral inner producted with Roman numeral, and so and then they will just appear here. And then so each of these basis vector a column vector representation of each of these orthogonal basis appears as the each column of this unitary matrix representation. Sorry that it is a little bit confusing, but that's the only thing I can say when I'm explaining about this relation. So this is relation between these two vector representation, and then they can be also summarized in this way. And one other thing you should also know is that if you want to obtain the new if you want to obtain the column vector representation of the same vector in the new orthogonal basis, all you have to do is multiply the Hermitian conjugate of this unitary matrix on the column vector representation of the original vector in the original orthogonal basis. Along the similar line, what you can also consider is the matrix representation of the operator, and then the same operator will be can be represented as the matrix, and then each of the matrix elements can be obtained by using this formula. And then if we want to find out the matrix representation of the same operator in different orthonormal basis, then the basis vector we have to use are different. So each representation will be different from each other, and the relation between these are also introduced in the lecture number 4. So these are the results we obtained in the lecture number 4. and then I'm going to use this relation in our discussion. Here, what I want to do is find a new representation of this matrix in a new orthogonal basis, and then another goal is I eventually want to represent this matrix similar in the form of the diagonal matrix. So as long as this is a Hermitian operator, the best option to make it diagonal matrix is to use the eigenvectors as the new orthonormal basis. So let's try to find out the eigenvalues and the eigenvector. And then for the time being, I will just ignore this 1 over square root of 10 factor for a simple quick calculation of the eigenvalue, and then I can recover it a little bit later. So the way we calculate the eigenvalue is by using the simple formula, which is the determinant of C minus lambda I should be 0 requirement. So that means that this will turn into minus lambda minus 1, and 2 minus lambda, and it is 2 minus lambda squared, 2 minus lambda squared minus 1, and then this should be 0. So that means that the lambda should be 2 plus minus 1, which is either 3 or 1. So that's the eigenvector, eigenvalue. And then let's also try to find out the eigenvalue corresponding to each of them. So for the 3 case, what I want is 2 minus 1 minus 1 2, and sorry, yeah, not this one. Yeah, so when I plug in lambda here, then it is minus 1 and minus 1, and then what and then under this case the eigenvector should satisfy with this requirement. So yeah, according to this one, that means that x1 plus x2 should be 0, or in other words, x1 should be minus x2. So according to, and then yeah, with this relation, what I can conclude is that the first eigenvector should be 1 minus 1, or maybe with the proper so it should be 1 and minus 1, and then with the proper normalization, yeah, it should look like this one. And then we will call this one as the first basis vector. And then another basis vector we have to find out is when the lambda equals 1. And then in that case, I should also follow the same thing. So like before, it should be 1 minus 1 minus 1 1, and then it will be x1 x2 should be 0 again. And then in this case, it is x1 equals x2. So the second eigenvector is 1 1, and then we should also normalize. So I will define the second a basis vector as this one. Now, yeah, what I have to do is, yeah, initially the C was not this matrix, but with this one. So if you just scale everything here, then it will turn out that it should be like this one, and then it should be also 1 over square root of 10. So that's what I just got here. And then now what I'm going to use is this relation, which says the matrix representation of the unitary matrix. In this case, is that the column should come from the vector representation in the vector representation or the column vector representation of the new basis in the old basis. And then similarly for, so each of the columns should come from there. And then once you obtain your unitary matrix in this form, then the original vector, original matrix can be decomposed into these relations, meaning that this unitary matrix will appear here, and then the Hermitian conjugate of this one will appear here, and then the the original matrix or original operator will appear in the and then in the center we will have the matrix which corresponds to the original operator in the new basis. Yeah, so this is the new matrix representation of the original matrix in the new basis. So by using the formula, yeah, the unitary operator, unitary matrix can be obtained by using the each of these components. So yeah, it will be 1 over square root of 2, but I know that each of these will come from these components, and then all of them will have the square root of 1 over square root of 2 in front of that. So let me just rewrite that it will be 1 over square root of 2, and it is 1 minus 1, and then the second column comes from this one, and then now it comes 1 and 1. And yeah, here what I'm trying to do is convert this one into the diagonal form. So I know that the C will be represented as the unitary, and then diagonal, and then unitary dagger. And then yeah, for this case, because what we have been doing is we started with the Hermitian operator, and then we found we tried to use the eigenvector as the new orthogonal basis, and then in that case we already know that the new matrix will appear as the diagonal matrix, and then the component of the diagonal components will come from the eigenvalues. So in principle, we are expecting that we will obtain the this diagonal matrix which has the 3 over square root of 10 as the first diagonal component, and then the 1 over square root of 10 as the second diagonal component. And then of course I want to make sure that our calculation is correct. So let me first calculate the let me just confirm that our decomposition is correct. So to confirm that, what I can do is calculate the first UD calculation, and then in this case U has the 1 over square root of 2, and then T has the 1 over square root of 10. So I can just start with the 1 1 minus 1 1, and then it will be 3 0, sorry, 0 1, and then I know that this will turn into square root of 1 over square root of 2, and then it will be 3, and then it will be 1, and then it will be minus 3, and then it will be 1. And finally, I want to calculate this with the U dagger, and then I know that it is square root of 2, and then this one has another 1 over square root of 2, so I just pull it out, and then well, or I can just do it later. So yeah, these are 3 1 minus 3 1, and then the U dagger is 1 over square root of 2, and then if any components here is the complex number, then I should consider about the complex conjugation. But here all those numbers are real, so all I have to do is transpose the components. So yeah, it is like this one. And then if I just combine these two, yeah, it will be square root of 10. And then uh, the result is that yeah, this one, yeah, so 3 times 1, which is 4. And then the second term is minus 3 plus 2, so it is minus 2, and then it is again minus 2, and then it is 4, like this. So is this the same as the C here? So yeah, what I what I know is that yeah, so we have the factor of 1 over square root of 10, and then yeah, they will cancel. So 2 minus 1, minus 1 and 2. So yeah, this is exactly the same as our original C. So yeah, C can be decomposed into this these three matrix product. So what I'm going to do is, if I replace the original C with this combination, then we will actually obtain very interesting result. Now, what I'm going to do is, this kind of form can be eventually turned into the this kind of um, uh, shape. So how can we do that? So yeah, the first thing I have to do is yeah, we realize that C can be expressed as D, yeah, U dagger, and then another thing is that if we have um, um, this kind of relation between the a matrix, then the ij component of this matrix can be expressed as the k and b I k and c k j. So if we apply this kind of relation to here, then what I can say is c cij is summation over k and l. Yeah, these are the dummy variable, and then we will have the u I k, and then this will be also as the k l, and then the last term will appear as the l and j of the u dagger. Something like, yeah, maybe I should, yeah, use the parentheses to make sure that we don't get confused. So this is one yeah, the expression for each of the component. And now what I'm going to do is, put psi was originally in the above. Yeah, it was yeah, so put psi is expressed as the ij, and then yeah, it was and then yeah, for our original case, it appeared as in this way, and then in that case there was no such a rule that whether yeah, so this I might change from 1 to 3, and then j might change 1 to 3 from 1 to 3, and then in this case this is the summation of all the possible cases. So this means that uh, 1 2 and 1 3 and 2 4 2 3 or 3 3, all of those kind of combination might appear in this summation. And now what I'm going to do is replace this relation to here, and then this will be the summation of all the possible I, J, K, L, and then now C will be replaced by these terms. So it is U sub IK, D sub KL, and U dagger of LJ. And now, yeah, I have these terms, I sub A and J sub B, like this. Now, what we can do is rearrange the factors. So you can see that the same I appears here and here, and then the same J appears here and here. So yeah, one type of the arrangement is that I can just keep the K and L, yeah, in the front, and then we will have KL, and yeah, if I just collect this, then they will appear as the summation over I, and then such a summation is I sub K and I sub A, like this. And then um, then the second term is the summation over J, and it is U dagger LJ, oops, LJ, and it is J sub B, like this. So these are the rearrangement of the term. And then, yeah, even though yeah, this might look like a summation of all the possible case K and L, but we know that when we converted the C uh, into this shape, we intentionally had this inner the center one as the diagonal shape. So even if these K and L might have any arbitrary combination, they are actually this term will be non-zero only when K and L are the same. So in other words, yeah, we can consider this one as K, just a KK, like this one. So and then the point here is now, yeah, I can show that. So these will be mapped into one set of the orthonormal basis, and these will turn into another orthonormal basis. And then yeah, so what this says is I U I K, oops, U I K, and it is I sub A. And then in this case, what happens is as we are changing the K index from 1 to N, and then indeed in this specific example, K goes to from 1 to 2. And then in that case, yeah, we will have one, yeah, so when K equals 1, then yeah, we will have some kind of vector, and then when K equals 2, we will have a different vector, and then I will show that these two vectors are also normal to each other. And similarly, this new combination of U dagger LJ and then the JB, yeah, they will also turn into other types of orthonormal basis. So they will just appear here, and then they are also orthonormal to each other. Now what I want to do is all those new form of the transformation of the vector with this kind of summation will generate the orthonormal basis, new orthonormal vectors. And then yeah, there are two shapes. One was the A part was appeared in this shape, and then B part appeared in this shape. So I will show that both of the case will generate the orthonormal basis. And then the first case is the proof of the first case is simple because we already have the definition of the unitary matrix in this form. So all I have to do is replace this one with this definition. And here it is I sub u sub ik. So it is replaced by ik. I capital K, and then here now it just turned out that this one looks like a completeness relation, and then this is actually the identity. So yeah, this will just turn into the K. And then here, when we started the definition of what when we started with the definition of this operator, yeah, all of these were supposed to be orthonormal basis. So yeah, this kind of combination will just turn into the with another set of the orthonormal basis. And with this relation, what I'm going also to, what I will also need is the reverse mapping. So I want to, once I have this relation, what I actually want to do is write down the original um, original orthonormal basis in terms of this new orthonormal basis. So yeah, what I can do is yeah, this original orthonormal, each of the original orthonormal basis can be rewritten by plugging in the identity operator. Yeah, so this is the summation of the all the new orthonormal basis. So this is the identity. So I can just add this one. And then now what I can do is, yeah, so replace this part with the definition of here. So if I plug in these things in here, and then now, yeah, because this is a cat and this is bra, so I should take the uh, um, I should consider the Hermitian conjugate of the entire part, and then now this one will turn into the cat, a bra, and then for this one, this one is just a scalar value. So yeah, even when I'm applying the Hermitian conjugate, their index location should not be changed, but only the value of this part should become just a complex conjugated. Yeah, so yeah, that's how, yeah, that's why I have this. And now this inner product is between the original orthonormal basis. So the this orthonormal base, this inner product will turn into the delta function, canonical delta. Sorry, not J. It should be, yeah. So this is delta I sub m, and now if this is the summation over m, so that means that the I here should be replaced by m, and then this term will go away. So yeah, this is almost the same, but now you know that the order of these are changed, because here it should become m u sub mk, but it is km, and then the reason is because we already had the star here. So if I change the order of these two indices, then it corresponds to the transpose of this one, and then transpose and the complex conjugation can be replaced by the Hermitian conjugate symbol. So that's why I can rewrite in this way. So if you want to represent the original basis in terms of the new basis, then this is a formula you should use. So yeah, I already proved that the first the formula for the expression for the a qubit is now this kind of transformation will generate the orthonormal basis. Another one, which looked like this one, will also generate the orthonormal basis, and then the proof is just quite simple. So all I have to do is define a new matrix V, which is defined as the complex conjugation of the unitary operator and unitary matrix. And then what I'm going to show is that this V should be another unitary matrix. And then to prove that something is unitary matrix, all I have to do is prove that the product of the V and its own Hermitian conjugate should become identity. And the proof is the following: because the V dagger is the same as the transpose of the original unitary matrix, because V was defined as the complex conjugation of the unitary matrix. So yeah, application of the dagger corresponds to a complex conjugation and then the transpose. But because there was already complex conjugation, so double complex conjugation just to generate the original value. But the transpose part still survives. So this is the equality between these two. And then because we already know that the unitary operator or unitary matrix should satisfy this relation. So even if I take the complex conjugation of the entire component here, they should still the same as the identity, because identity is just a real valued matrix. So, but if I apply the complex conjugation to the entire part, then the complex conjugation will be applied to each of the components. So this unitary matrix will be changed into complex conjugation of the unitary. But if you apply the complex conjugation to the to the Hermitian conjugate, then this will just turn into the transpose. So and then here I already defined the V as the U star, and then here I also showed you that the U transpose is the same as the V dagger. So yeah, now this equality can be replaced by this one. And then this relation shows that the V is actually the unitary matrix. Now, because the V is the unitary matrix, so this kind of linear combination of the original basis vector corresponds to the multiplying the V sub JIL to the J, and then the summation over J. And then now we know that and then the only difference here is that the dagger is gone, but they are also the order of the indices are changed. So here now this is exactly the same shape as this one, and then we already know that this kind of combination will generate the orthonormal basis. So and then this one is exactly the same as this one. So the result of this combination will also produce the orthonormal basis. So that's how we can know that this kind of mapping will generate another set of the orthonormal basis. Now, similar to here, I can also consider how we can represent the original orthonormal basis in terms of the new generated orthonormal basis, and then the relations are the same, except that for this one and this one, they have the difference of the complex conjugation. So this is the result, and then I'm going to use this result for the for further discussion. Now, by applying the all the relation I just derived in the slide, so I can use this one to find out each of the components. So let's say that let me find out the new orthonormal basis, which will diagonalize the C matrix like this one. So according to this definition, then the one is just taking out the because this Roman numeral notation corresponds to the column number. So all I have to do is pull out this first column and then apply to each of the original vector. So it is 1 over square root of 2, and it is 1a, and then it is minus, sorry, not plus. It is minus 1 over square root of 2, and it is 2a. And for the second case, it corresponds to the second column. So it is 1 over square root of 2, and then the 1a, and this is the 1 over square root of 2, 2a. And the reverse relation corresponds to this relation. So what I know is that the 1a can be expressed as this is the Hermitian Hermitian conjugate of this one, but because that all of them are real, we don't need to consider about the complex conjugation. But that one probably that one just corresponds to a transpose for this specific case. So all I have to do is, yeah, for the one case, yeah, I have to pull out the first column of the transpose, or I can say that first row of this guy. So that corresponds to the square root of 2, and then it corresponds to a, I sub 1 sub a, and then that is the square root of 2, and that corresponds to 1 sub 2 sub a. And similarly, 2 sub a corresponds to the second line. Now it corresponds to 1 over square root of 2 I sub a plus 1 over square root of 2 and 2 sub a. So this is the relation for the a particle. Then what about the b particle? Yeah, we will just continue to find out that. So it is the b case. Now what I have to do is calculate, consider the transpose of this one, and then with this index, and then now it actually the same as the before. So yeah, this constant L corresponds to the constant column in the not transposed case. So for this one, yeah, so actually they will be exactly the same as this relation. So yeah, it is yeah, like b minus 1 over square root of 2b, and then the 2b is the 1 over square root of 2, and 1b minus 1 over plus, now it is square root of 2b, and the result of this will be also the same. So I won't repeat here, or I just can copy for the entire thing, and then they will be the same, and then the only difference I have to do is replace each of these as the b, not the a. So yeah, it is b, 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 and so forth. So yeah, these are the relations. Now why did I bother to change all of these in terms of the a and this Roman numeral a and b? That's because I actually wanted to show that the original relation, which was shown here, can be actually transformed into the summation of all those orthonormal, new orthonormal basis. So here, what I'm going to do is replace each of these with this new definition. But let's save some effort so that I can make the situation a little bit simpler. So before I jump, instead of replacing all of them, let me just start with this effort, because now you can see that these two terms has the common factor of a sub 1 sub a. So what I can do is I can just combine 1b and then minus 2b like this. And then similarly for the second term, what I can do is combine these to collect these two, and then it will be minus 1b plus 2 times 2b. And what happens here is that if I replace each of them like this one, then this term will be the same as this one. And then if I multiply 2 here and then subtract from here, then then that corresponds to and then 1a, but then and there is a square root of all of them has the square 1 over square root of 2 in front of them, and then it corresponds to 2. I multiply 2 for each of them and then subtract them, so that corresponds to 2 plus 1, so it will be 3 1b, and then it will be 2 minus 1, so that corresponds to 2b case. And similarly for the second term, now I multiply 2 and then subtract from here, subtract this line from the second line, so that is minus 3. Oops. I should not forget about the 1 over square root of 2. So it is minus 1 multiply 2. So that is 3 with the I sub b, and then 2 minus 1 corresponds to 2b. And now I have the 1 over square root of in front of both of them. So I can just rewrite as 20, and then it corresponds to a and 3. And then let me just also work a little bit further. So now I can see that this one and this one are the common factor. So now what I'm going to do is factor out with the I sub 1 sub b, and then the factor out the that was not number 2 Arabic number 2, but it is this one. So so now what I'm going to do is also collect these terms together. So and then here what it should be replaced is 3 times 3 1a, and then from here it comes from 3 2a. And what about the second term? Now it is 1a, and then this one is multiplied 2 here, so that is 2a, like this one. So you might feel like I didn't do much of the thing, but it is actually interesting that this one, these 3 factors are the common. So if you just pull out, then it is 1 sub a minus 2 sub a, which corresponds to this line. So this one, they are the same, except that I should consider about the square root of 2. So it can be replaced by 3 square root of 2 with the I sub a and this term I sub b. So this first term is replaced by this this term. Oops. Okay, and then for the second term, it is actually 1 plus 1 sub a plus 2 sub a, which corresponds to this second case. And then I should not forget about this one, but then it can be also replaced by this, and then I should not forget about this term, which is the b. So eventually what I showed was that And then yeah, I can cancel out this square root of 2. So it is well, yeah, so what I can say is that the first term is 3 over square root of 10, and it is a sub a and I sub b. And then for the second term, it is just 1 over square root of 10, and then it is I sub a, and sorry, not I, but Roman numeral 2 for a and b. So this is exactly what I was looking for. Initially, I started with this kind of formula, which has all the possible combination of 1, 1 and 1, 2 and 2, 1 and 2, 2. But by going through the clever basis transformation, I actually turned the entire quantum state into this form, which, and then this is and then here the most important property is each of, yeah, so the A A system can have both the one vector and then two vector, which are the orthogonal to each other, and then the second system, which is the B system, also has another set of the orthonormal basis of 1 and 2. And then the point is, when we write down the entire quantum state, then the first vector of the first orthonormal vector of the A will be only appear with another orthonormal basis of the B, and then the same this same basis vector won't appear in the rest of the term. So that is one way to determine whether some system is entangled or not. So I can summarize what I have been doing in this way. So we started with this some arbitrary looking quantum state, and then we intentionally wrote down from all these coefficients. I intentionally created a new matrix, and then because this new matrix turned out to be a Hermitian operator, a Hermitian matrix. So I realized that I can actually diagonalize this kind of matrix, and then this was the unitary matrix I needed to convert this one into the diagonal matrix. And then once I apply this unitary matrix for the decomposition of this C matrix, then it turned out that all the combined state can be rearranged, and then eventually the final state can be expressed as the summation of these two components. And then in this case, the first vector in the A corresponds to the first vector in the B, and then second basis vector A corresponds to only the second basis vector in B. So, and then this is exactly the shape of the entangled state. So by converting any of the given state, then you should be able to show whether the given state is the entangled state or not. The problem is, here I intentionally chose this kind of a state, which can make this matrix as a Hermitian. However, more general situation is that you will only have this kind of state, and then if I just do the same thing, then the new matrix is not Hermitian. So what can we do? Yeah, so the method we have been using was very useful if this was Hermitian, but it cannot be directly applied to here. So did we waste our time? Of course not. Yeah, so yeah, in the next lecture, I'm actually going to show that even if this matrix is not the Hermitian, any arbitrary given matrix can always decompose into the product of the unitary matrix and the diagonal matrix and the unitary matrix. So and then with such kind of generalization, you will realize that you can always convert any given a quantum state as into this kind of shape. And then for such kind of conversion, we will need to use the something called as a singular value decomposition. And then I will also cover what is the meaning of the singular value decomposition in the next lecture.